Introductory to Calc. Hope you all are having a fantastic day. Today we're moving on to 2.5, which introduces the second derivative. So far we have talked about how the first derivative, which is just f prime, it finds like the slope of the tangent line of the curve, and it could find like instantaneous velocity of a particle, stuff like that. So today we're going to talk about what the second derivative is and what it tells us about a graph, and determine what intervals have a positive or a negative second derivative. We're going to talk about what an inflection point is, because if you haven't heard that term before, you'll hear it a lot in calculus. And then whether the graph is concave up or concave down, and then interpreting the second derivative as a rate of change. Okay, so we're going to start with just the definition of the second derivative. So the second derivative is literally you have the function, and then you take the derivative of that, and you get f prime, or the first derivative. And then if you take the derivative of the derivative, right, of f prime, you get the second derivative. And a lot of times we call that f double prime, and we have f with two apostrophes in the middle. And I'll show you how to use the other notation as well. Okay, so notation is if f of x is a function, then f prime is the first derivative, which you already know, and f double prime, which is two little apostrophes, is the second derivative. And then remember how I taught you about this dy dx notation, right? That just means like the change in y over the change in x, delta y over delta x. For the second derivative, you throw a 2, like a squared on top of the d, and a squared on top of the x, and all of a sudden that means the second derivative. So I included that in the notes there. That's all that is. It's d squared y over dx squared. It's just another notation for the second derivative. Notice that second derivative has two apostrophes, or has the squares. That's a good way to like tell that it's the second derivative. And how to find it is you just take the derivative of the derivative. Simple enough. Okay, so the other thing, other term that you need to know is concavity. And hopefully from other classes, like this is not the first time you've heard this term, but concave up means it's like shaped kind of like that, and concave down means it's shaped kind of like that. And the way I remember concave up and concave down is I think of a bowl of cereal. So my concave up, I'm happy, I'm up, I'm positive, and my cereal's in my bowl, so I'm a happy person. And then when I'm concave down, I'm down for the day, and I'm bummed, and it sucks, and I'm negative, and I'm feeling bad, and I'm concave down because my cereal's spilled all over the floor. So this is concave down, and this is like concave up, okay? So I will draw a graph of that, but I just remember cereal. That's kind of the way that I remember. Okay, so that's concave up, concave down. Some functions are all concave up, and some functions are all concave down, but you might have a function that changes from concave up to concave down. So for example, this function, for the first section there, right, from like here all the way up to about there, it's all concave up, and I would have like all my cereal is sticking in the bowl there. But then, sorry, somebody just came over the speaker. Okay, anyways, so here your cereal would still be in the bowl, but here your cereal is all over the floor. So it actually changes from concave up to concave down, and the point at which that happens, right here, is called the inflection point. Okay, so that's an important vocab word. Okay, so there you see concave up here, concave down here, and that is an inflection point. Okay, the reason that we need to learn this stuff is because this is related to the second derivative. So so we're just kind of like as a quick refresher here. If f prime is positive on an interval, so if f prime is greater than 0, then we know that the function is increasing. Similarly, if f prime, oops, that was a total oopsies. That's supposed to be negative, okay? So if f prime is negative on an interval, then f of x is decreasing there, right? It's going down. So it should look like it's going downwards. So if you think about what f prime means, or the derivative, right? And I take the derivative of the derivative, then basically f double prime, if it's positive on an interval, then the derivative is increasing. And what that means is like the slope is getting bigger, right? Which means it's like scooping up, which means it's concave up. And if double prime is negative, then that means the slope is decreasing, right? That f prime is decreasing. So the graph of f actually is like, it like starts steep and then it starts to kind of like smooth out. So that means that it's concave down. And that's why the cereal bowl thing, I think, makes sense, because if f double prime is positive, then you're positive because your cereal is in your bowl. Like, you feel good, you're happy. And if f prime is negative, then your cereal's all on the floor and you're having a really bad day. So negative is bad, and then positive is good. Good cereal, bad cereal. Concave up, concave down. Okay, hopefully that makes sense. Anyways, so we're gonna talk. So we're gonna like look at an example. So here it asks, on what intervals are the following true about the given functions? So we're gonna look at A, and we're gonna answer A, B, C, and D about A. And then we're going to answer A, B, C, and D about B, and the same thing about C. So I'm going to like explain the first one, but then again, I think you should try the other ones on your own, and then just check with my answers in a minute. Okay, so first problem. This is f of x that we're looking at, and the first question is, when is dy dx greater than 0? So this is, look at your notation. This is your first derivative. So this question is asking, when is f prime, or the first derivative, when is it greater than 0? And that is, when is the function increasing? So you can kind of look at this function and it's decreasing here, and then it's increasing here. So what that area that I highlighted there, that's where A is increasing. Where f of x is increasing. And then B is asking where is it decreasing, and that would be on the other side here. So if I'm asking like for what x values or on what interval is this true, we would need to know what this is, what value this is, because it's increasing or it's decreasing before it and it's increasing after. So I would probably, let's pretend that number is 3 or something. So we would say that the function is decreasing from negative infinity to 3, and it's increasing from 3 to positive infinity. Okay, so then the next two parts, C and D, are asking why is this a typo? Why am I so bad at typing stuff? This one should be negative. I'm not asking the same question twice. So C is asking, when is d squared y over dx squared, or f double prime, right? That's the same thing as the second derivative. When is it greater than 0? And in this case, right, we want to look at, for f double prime, we want to look at where is it concave up. That's when f double prime is 0. It's positive. So in this particular case, this is always concave up, right? Your cereal is always in the bowl here. And so this is from negative infinity to infinity. It's going to be concave up, which means that there's no places where it's concave down. So there you go. Okay, for this graph, for g of x, dy dx is positive if the function's increasing. So this is actually increasing everywhere, right? It goes from low to high. But the rate at which it's increasing is decreasing, right? So like that means that it's steeper here and then it kind of like levels off here. So that means that the derivative everywhere is negative. You're always going to have, like, if I finished my bowl, right, all of the cereal would be on the floor. So in this particular function, dy dx is positive from negative infinity to positive infinity. There's no places where it's negative. The second derivative is always negative. So C, there's no answer. D, it's from negative infinity to positive infinity. C is the only one where it changes from in concavity. So A, again, is asking where is it increasing? Well, it's increasing from here to here and from here to here, so it's basically increasing everywhere. So that means it's decreasing nowhere. That's what B is asking. C is asking where's it concave up? Well, in that case, right, again, you want to look at where is the slope increasing, right? And that's on the right-hand side. So that's C in this case. And then D is asking where is it concave down, and that's going to be on the other side of 0 there. So negative infinity to 0 would be where the answer to D, and then from 0 to infinity would be the answer to C. Okay? Hopefully that makes sense. Okay, so we've got a couple examples. This one, a little bit the words got cut off, but it just says a population P growing in a confined environment often follows a logistic growth curve. So that means using logs, if you've learned logs and exponential functions. Like the one shown in figure 2.45, relate the sign of d squared p over dt squared to how the rate growth of dp dt changes over time. What are the practical interpretations of t0 and L? So keep in mind that y is the population and t is time. So in this case, right, I highlighted where the function is concave up, right here, before t0, and then it's concave down after t0. And that basically, like, if you think about a population, right, it will start increasing really quickly, but then something happens where it kind of has to, like, level off, right? There's only so large of a population that most environments can sustain. So usually what happens is there's a limiting population where you use all the resources that are available and the environment can't sustain a population that's larger than that. So T0 is kind of where that changes from, like, ooh, it's a new population, like, let's pretend it's rabbits, right? The population of rabbits is, like, increasing like crazy, and then all of a sudden they kind of start to run out of food resources or whatever it may be, and so they kind of have to, like, level out in terms of their population. So then last but not least, I just want to talk about, like, the positions and velocities. So if you have a function that is the position of an object, then the velocity is the first derivative, f prime, and the rate at which the velocity changes, which is also acceleration, is the second derivative. Okay, these are all fancy ways of writing the same thing. The velocity is the derivative of position, and then acceleration is the second derivative of position or the first derivative of velocity.